Three, two, one. Okay. All right. I'm here. I swear. I'm actually still alive. Oh my god. All right. So I'm probably gonna be coughing a lot through this. I'll try not to. But all right. Let's get to it. All right. Uh, Start up where we were planning to start on Monday, but obviously illness has decided to keep going because and the fun doesn't stop. Um, All right, and we're not going to stop having fun. Instead, we're going to start really digging into Matrix operations. Last time we wrapped up the story on some of the geometry that we can do in Euclidean space using the dot product for the reals, the inner product for the complexes. Again, we primarily are focusing on real things, but we will dip our toes in the complex plane here and there. And goal for today and the next section is to really dig deeper into matrices, which again were objects we've already set up for dealing with systems of linear equations, but we're going to kind of now study them in their own right and um, get a feel for them. All right, so let's get right to it. So recall that a matrix is an m by n array of math objects. Again, for us, they're typically going to be real or complex. The set of real matrices, I will use this notation. The set of complex matrices, I'll use this notation. It's worth noting that our book uses this notation, which kind of just lets you go, oh, it's real when you want it to be real, and it's complex when you want it to be complex. This is a popular notation for matrices. It is used. I like using this notation because it matches better with kind of the notation we use for Euclidean space, and there is a direct connection between matrices and Euclidean space. So thematically, I feel it's better. And again, remember in math, right? We don't argue about what a matrix is. We all agree what a matrix is. What we're going to argue about is the notation that you're going to use for matrices. And oh boy, people got opinions. So, all right. And speaking of that, let's talk about how you represent our elements of the set of matrices. I'm going to use bold symbols for the matrices. The entry in the J-Fro and Cave column, I will denote that by our matrix, then with a subscript of J, comma K. Some people leave the comma out and kind of leave it up to you, but that can be a little misleading when J and or K have, two digits, so it might not be quite clear what it is. It's worth noting that the textbook does this notation where they kind of put a bracket around A. That is a very common notation as well. I think it gets a little overly notative, so I don't like to use it, but it does have its advantages, especially if you have like a sequence of matrices, and so it's like, where do you put that symbol here? Yeah. But I'll leave it without the brackets, but if you are following along with the text, that's the notation they'll use. And right, these are rectangular arrays, so I can write them out as a rectangular array. So sometimes we'll write out matrices like this. When it comes to proofs, we'll try to directly work with the entries as needed. As we'll see today in a couple of the proofs, it becomes a huge exercise in subscript management. So sometimes matrix proofs just go better by actually writing out the array and go, this is what's happening. So we'll jump between the two. All right. Before we go any further, let's note that matrices are equal precisely when their entries are equal. And it goes without saying, right? Two sets are equal if they have precisely the same elements, right? Two matrices should be the same if they have precisely the same entries. Worth noting. All right, and speaking of that, let's make some more notes. I've got notes. So one thing that I'm going to do, this is pretty standard, is that the set of n by 1 matrices, so a matrix that just has a single column, right, note it's a row column in the setup here, the m by n. So a matrix with one column is really like an element of Rn, so I'll treat them as the same. R1n can also kind of be viewed the same, but there's sometimes an advantage to think of that as a different thing, like differentiate between a row vector and a column vector. There are these occasional equations that kind of like require you to have the two, but we're going to not get too sweaty about that. So, as far as I'm concerned, n by 1 matrix is the same thing as an element of Rn. They're technically different in a way, but they're basically the same thing. As we've already discussed, if you have the same number of rows and columns, you're called a square matrix. Now, here is a notation that I use that's not super standard, but it's something you have to address. So given a matrix, we're interested in its entries, but we're also interested in the individual rows and the individual columns. Right, we've already seen row operations play a very important part here, so I'm probably going to want some notation for what the rows are. Right, we've even seen converting a span to a row space was a very powerful tool, so having a notation for the rows of a matrix is going to be helpful. And, as we've also seen, a linear combination of vectors is really a linear combination of columns of a matrix. Right, every system of linear equations is really dealing with a span involving the columns. So the rows and the columns of a matrix are very important and useful, and so we're going to have some sort of notation for it. And this is a notation that I saw on Math Stack Exchange that I thought was really clever, right? Because it's like, hey, the j row is locked down, and then the k column can be whatever it wants. Likewise, the k column is locked down, and then the row entries can be whatever they want. Right, so to give an example of kind of how this works, if this is my matrix, 1, negative 2, 3, 0, 4, 0, right, then its first row is the vector 1, negative 2, 3. Its third column is the vector 3, 0. So our book doesn't really use this notation. Other books kind of use a similar notation. When we deal with matrix multiplication, which is what we'll talk about next time, it's going to be a very powerful tool to have this notation because it's going to let us basically write matrix multiplications as dot products of rows and columns, and that's going to make a lot of proofs super easy. So that's just kind of what we're going to do. All right. So again, this is a crazy person notation that I use that isn't standard, but it pops up in some other textbooks. So, okay, just as we have a zero vector, we'll have a zero matrix. So the matrix consisting of all zeros. No, nothing surprising there. Similarly, we have a negative of a vector. We can take a negative of a matrix just by negating all the entries. So obviously, with these two in pocket, we know where we're going. And let's go ahead and recall our friend the identity matrix. So the matrix where we have 1 on the diagonal and 0 elsewhere. Note now, we have some new context for this. The columns are the standard unit vectors, so are the rows. And as we noted, we may include a subscript to indicate the size of the identity matrix. So if I want to talk about the 2 by 2 identity, there it is. And if I want to talk about the 3 by 3 identity, there it is. Cool. Right, again, we've already seen the identity matrix. We've already noted that these are very important. The matrices that are row equivalent to the identity matrix are very essential. They have very incredible properties. And when we talk about matrix multiplication here in a moment, we're going to see exactly why this is so powerful and useful. All right, so goal for today is matrix operations. We've now sort of gotten matrix notation on lockdown, and we've got some special matrices. So let's go ahead and talk about how we can scale and add matrices. And again, it's just how you scale and add vectors. It's done component-wise. So, for example, if I wanted to scale the matrix 1, negative 2, 3, 0, 0, negative 4 by the scalar negative 2, you just do it. And if I want to add matrices, you do what you think you should do. Nothing weird happens. So scaling and adding is entry-wise, and it comes as no shock that everything that we saw in Rn is also going to fly for matrices, right? So again, note here, right, we're creating the definition of addition of matrices from scratch. So I don't know that all of the usual addition things work. I need to actually prove these. Now, I'm not actually going to prove any of these, and I'll just say the proofs that we did in Rn, it's the same proofs, just you have 2 subscripts instead of 1. It's nothing shocking. Right, but all of our usual friendly addition properties hold. We have our associativity, we have our commutativity, we have our identity, we have our inverse. Scaling also behaves nicely. It has the distributive property. And then we have the conversion property. So again, note this is the summation of real or complex numbers. This is the summation of matrices. Right? This is the multiplication of scalars. This is the scaling of a scaled entry. So these two, while distributive looking in nature, are actually communicating a bit more of a subtle fact. And of course, scaling by one doesn't do anything. Okay. All right, it's worth noting that some of the things that we've proven for Euclidean space operations are going to carry over to matrices. Multiplying by zero does what scaling by zero does what you think it should do. Scaling by -1 does what you think it should do, so on and so forth. Right, but I don't want to beat that dead horse any further. We're going to talk about vector spaces soon, and we'll formally prove that those facts hold in any setting where you have scaling and adding at your disposal. But let's actually truly talk about a matrix-specific thing, right? A real, honest to goodness, this is a matrix-only move, and that's this idea of transpose. And so, first of all, absolutely baller symbol. I love it. So in LaTeX, this is /top. It's great. It's up and top. It's awesome. I love it. It's cool. And what does it do? Well, it swaps the rows and the columns. So the jth row, G becomes the jth column. Column becomes the kth row. Right, so visually, if you want to see what it does, it takes the matrix 1, 2, 3, 4, 5, 6. Row 1 becomes column 1. Row 2 becomes column 2. Row 3 becomes column 3. Now, at first glance, this does seem like okay, yeah, sure, buddy, you can do this. But you're going to be, baffled at how powerful this is, right? It's like, yeah, just swap my rows and my columns. And, truly, it's something that you can only do for a matrix, right? You need rows and columns to swap them, so it's truly a matrix move. But we're soon going to talk about the fundamental subspaces of matrices, and transpose lets you get away with such an insane move. You're not going to believe how powerful this is. And at first glance, when you first see it, it's just swap the rows and columns. And it doesn't seem like it really does anything, but I'm telling you, this packs such a punch. It's crazy. Oh my god, yeah. Okay. All right, that being said, let's actually do some proofs. So, I got 3 facts for transposition for you. Transpose the transpose, you're back to normal. Transpose a scaled matrix, it's the scaled transpose. Transpose a sum, you get the sum of the transposes. Transposi, or transposites, whatever the correct pluralization of transpose should be. Transposes. All right, so the first one intuitively just makes complete sense, right? If I swap the rows and columns and then I do it again, yeah, you're back to normal. And these also should make some sense because, well, if I scale everything. So if I swap my rows and my columns, well, they're all already scaled, so when I swap them, they're still going to be scaled. And same thing for the addition. The addition is done entry-wise, so when the rows and columns are swapped, then, it's still going to work, but let's formally work through the details of the proof. And again, right, it is this sort of index management sort of thing. Right, I want to prove that this matrix is equal to that one. Well, look at the jk entry of this matrix and show me that it's the jk entry of that one. Right, and unravel the definition. First transpose says to swap j and k. Next transpose says, well, do it again. Hey, there you go. And then similarly for scaling, right, the transpose says to swap. The kth j entry of a scaled matrix is the scaled k jth entry. Well, we know that's the j kth entry of the transpose, and then since that's being multiplied by alpha, that's then the k jth entry of the scaled matrix. Right, we're familiar with these sort of maneuvers. We did this with Euclidean space, so right, this is a very familiar style proof. And then the same thing is true for addition. Nice. Right, so no, I'm not going to verbally walk through the proof here, but right, you get the picture. All right, well, so that's actually really neat here, and and this is worth sort of dissecting a little further. So first of all, transposing undoes itself. That's a very neat little property. But note that transposing respects scaling and respects addition. Scaling and addition are the two fundamental operations so far for matrices, and here this new third operation interacts appropriately with them. It keeps those element-wise transformations undisturbed by their actions. I wonder if that's an absolutely fundamental fact of linear algebra, and perhaps you've seen this sort of thing before, like, I don't know, scaling a derivative uh, or scaling an integral behaves nicely, or the summations of derivatives, or the summations of integrals behave nicely. Perhaps you've seen that, or maybe you heard it called linearity, and we might get to that soon. Okay. All right, so there we go. We've got our first truly matrix maneuver. We've got a nice little proof for it. And now let's wrap up our introduction of matrix operations by heading on over to the complex world and talking about a complex matrix specific move that we're going to use like in exactly one spot, and we absolutely need it because it's going to make this one proof super easy, and without it, it's like impossible to prove it otherwise. But the buy-in is a lot because we got to set up a lot here with the complexes, and we're going to do this like utterly disgusting looking proof. But we need it because it's going to like make this one proof about eigenvalues like a one-liner. So we're just going to do it. All right. So what's something that's complex number specific? Well, that's conjugation, right? So I can conjugate a matrix by just conjugating its entries. So for example, if I had the matrix 1, negative I, 1 plus 3i, 0, and I conjugated it, well, I just conjugate the complex numbers, right? The real numbers are unaffected by conjugation, because again, it's reflecting across the real axis. And then the complex numbers, the imaginary part is negated, giving me that. All right. And we already know that complex conjugation is also undoes itself, right? So if you conjugate a conjugate, you're back to normal, right? Reflect across the axis twice, you're back to normal. We know it respects multiplications, so it will respect the scaling. And we know it respects additions, so it will respect the sum of matrices. So you can formally work out the details of that proof if you really want to. Again, it's going to be some index management. I don't want to write them out here. It's not particularly exciting, but if you're so interested, and our textbook does go through the details of the proof, and their details are very similar to my details of these sort of proofs here. So if you really want to see it, go for it. Okay. All right. So the real money now is combining the two previous ideas into this notion of what's called the adjoint of a matrix. It's the conjugate transpose of your matrix. So you conjugate your matrix, and then you transpose it, and you denote it by A star. And I don't know what it is about this particular notation. This always makes me think like I'm doing something crazy. Right, I don't know what it is. I just think this notation is like super cool, and it's like forbidden. It's like super insider math knowledge. Like if you're adjoining a matrix, you're really doing some shit, you know. It's like when you're doing like line integrals and you do the integral with a little circle in it. It's like that when when you got that stuff flying around, you're doing some. You're seeing some serious stuff there, you know. But again, it's just conjugating and transposing. So, for example, the matrix we just conjugated, if you want to take its conjugate transpose, well, then you just transpose the matrix. So the first column becomes the first row, and the second column becomes the second row. All right. All right, so let's wrap up today. Before I'm like totally just gotta get on a ventilator or get on some oxygen or something, or feel my lungs just giving up. Oh my god. I don't know what disease I got, but it's awful. Oh my god. All right. Anyway, so let's wrap up today with some quick proofs about how conjugate transposers behave. Like I said, we're going to prove one thing that's pretty disgusting in terms of the details of the proof, but it's going to be an essential move for eigenvalues later on in the course. All right, first things first, we're going to prove that the definition of adjoint is conjugate transpose, but you can actually do transpose conjugate and get the same thing. Obviously, transpose conjugate doesn't exactly roll off the tongue like conjugate transpose does, so that's why it's traditionally done like that. But you can reverse the order of operations there. Adjoint respects addition, and it respects a scaling, but note it will conjugate the scalar. So recall, we kind of saw that happen with inner products in the second component. Yeah. Adjoining an adjoint gets you back to normal, and then finally, and this is the thing I was referencing, adjoint has this absolutely insane property that if you look at the inner product of A, Z, and W, it's the same thing as the inner product of Z, adjoint W. Ooh, check that out. So if you know something about eigenvalues, you know that this is equal to a scalar multiple of Z. So you can probably see the power of being able to also move it over here and kind of have these Z's match up. Yeah, right? Yeah. Okay, and side note, we're moving a little forward. I forgot to mention this when we first talked about inner products. I have inner products defined backwards from how our book does. Our book has inner products defined the way physics usually defines inner products, where the conjugate scaling is happening in the first component rather than the second. And that's dumb and stupid, and don't do that. So I have it defined for the second. So my inner product stuff is always going to be reverse. So our textbook will have these results, but they'll have the inner products flipped. It's because they've defined it essentially as the conjugate of what I would normally do inner products as, where the first component is the normal linear part, and then the second component has the conjugate piece. Just to be aware of. And again, don't get too crazy about this. We just need this every so often. It's not our main focus, but like I said, there's going to be, especially when we get to eigenvalues, because a lot of that's built off of polynomials, and polynomials just need complex numbers to just behave. So as you'll see, we're just going to need it for like this couple of things, and it's just, we just need to have the setup so when we get there, we're not like blindsided by it. All right, well, let's quickly go through these proofs again, so I can lie down for like a few hours. All right. Okay, and again, the proofs are very index management-y. Just write out the definition. What's the JK entry of this? All right, well, the transpose lets me flip it. Then I can conjugate. But here in the conjugate, I've got the flip, so I can turn it into the transpose, and then I got the conjugate. Right, and the adjoint of a sum is the conjugate transpose. Conjugation breaks up over addition, so does transpose, so it all pulls apart accordingly. Transpose adjoint a scaled, you're doing the conjugate transpose, conjugate breaks apart, transpose breaks apart, it goes the way you want it to. Right, and if you adjoint the adjoint, well, then you're adjoining, then you're taking the conjugate transpose of the adjoint, well, then you got the transpose conjugate, so the conjugates knock each other out, the transposes knock each other out, and you're back to the original matrix. Okay, now for the brutal computation, this one right here. Okay, you just got to write it out. Okay, so recall, what is the inner product here? All right, well, it's the normal dot product where you take the entries, multiply them up, add them up, but you conjugate the second one. So again, like I said, that's the way I've defined it. Our book conjugates the first one. It's the same thing, it's just going to be written backwards. All right, so then you just got to write this out and pull it apart and just keep track of every step. Okay, right, so what's the kth entry of this? And I just realized I jumped the gun here. Oh no, I didn't actually define this yet. Ah, damn it. Oh, spoilers. Oh no. I was too excited. Oh my god, I didn't define what A times Z is yet. what a silly thing to realize at the end of this video. Yeah, again, I'm not exactly thinking straight here. Oh, well, you know what? You know what, then? Well, we're just gonna save this. Yeah, you don't know what this is yet. Oh, I was too excited. The book didn't do it, and I was like, oh, the book didn't prove this yet. It's like the most important thing ever. And then now I'm like, oh yeah, because you didn't define it yet. What crack am I smoking? I'm smoking that a number one product. That's what I got going on here. All right. Well, you know what? Ignore everything you just saw. We'll return to that computation. We'll revisit that. Pretend you didn't see nothing. There you go. Hey, it never existed. Neuralizer yourself on that one. All right. Hey, Annie. Okay. Well, great. Good. All right. We can cut the video short here. That's silly. Shit. Totally blanked. Yeah, we haven't defined that yet. We'll do that next time. All right. Great. Anyway. All right. What a silly way to end the video. Okay. Well. Okay. I'll see you in person. We'll start talking matrix multiplication next time.